No, back
Works.
again.
What was I saying? Now, you can have, if you jump with the same height, what does that tell us about impulse? Vertical direction.
Same.
It's the same, right? Now you can do it a couple different ways. Some maybe it is going to be more like this or one more like that. But if you jump the same height, you're going to have the same impulse. Why?
Because there's the same.
What's that?
The same impulse. You have
Because
Same
mass
weight
and
and same
time
time.
and force are equal.
Not necessarily. One time you can produce a lot of force, another time you can produce a little bit less force, but you're able to do it for a little longer.
impulse could be
Because of the
fast.
acceleration of gravity.
That's
probably.
exactly right. Because of the acceleration of gravity. Negative 9.81. Same reason why when you start from the same height and land, your impulse or your initial momentum is going to be exactly the same. All right. Questions?
Yeah, so there's one, like he's jumping with more flexion, knee flexion or something, which would be like the second one.
Good question. I don't know.
Okay.
There could be a lot of different things that they're doing differently. I mean, we could speculate.
But those are like two jumps from the same.
Maybe one they're going down a little bit faster or slower, or there's a lot of different things that could be
Okay.
happening.
Okay.
My guess is this one they're going down further, they're doing a greater knee flexion, just because the little is greater than this one right here.
But those ones we're supposed to assume are the same amount of area under the.
Doesn't really matter.
Okay.
If they are the same, that tells us that they jump to the same height. Okay. So based on this, force time graphs from a force platform from a high and a low vertical jump. So which one's the high vertical jump? It's going to be this one right here, right? Because the impulse is greater. So this area is going to be greater than this area. So if I put two graphs on there, I could say which jump was higher, and you'd be able to say, oh, this one. I'll make it obvious though. You're not going to have to like fill in little. Yeah. Okay, so once again, we're saying that impulse is going to be. Even if you have the same impulse, you have two completely different scenarios. Right here, you have the same impulse, correct? 2 times 10, 20. 2 times 10, 20. So impulse, although constant, can be saying two very different things. We talked about landing, so I'm not going to go ad nauseum about the landing. When you go from the same height and you land, the impulse is constant, but what can change? Soft landing, stiff landing. Which one has a greater vertical impact or greater vertical force? The stiff landing. Because even though the change in momentum is constant, what is not constant? These are not necessarily constant, right? So a stiff landing, your decrease in time, which has to do what? Increase force. When you flex those knees and hips and ankles, what? You're increasing the time, so what has to happen? All because your change in momentum is constant because you're going from the same height. They did a research project with female volleyball players, and what they found is the female volleyball players have really high vertical force, and so they trained them to bend their knees quite a bit more, decrease that force quite a bit. We looked at foam rolling, the influence of foam rolling on landing mechanics. What we found is landing mechanics, they're increasing knee after foam rolling, they have increased knee flexion and hip flexion, and one of the legs has increased dorsiflexion upon landing. So what would you assume if they're jumping at the same height? What would you assume about their vertical force?
Less.
It would be less. For some reason, we're not finding that it's less. And it's very perplexing and trying to figure out why it's not. Anyway, Kristen Rollis did that project this past spring, and she's submitting it to the American College of Sports Medicine. That's a big deal. If your foam rolling is not doing anything for performance, but what it is doing, when you, after foam rolling, you have increased knee flexion. From an athletic training perspective, would that be good?
Yes.
Yeah, because supposedly it's supposed to decrease that force. Is it doing that? No, not yet. We need a bigger sample size. But even though there's no sports performance related with the foam rolling, increased performance, if it's increasing flexion, range of motion, it may decrease injury risk. All right, example problem. Can the baseball be stopped? Okay, baseball traveling, we're going to look at that one because I need the board to do the problem. So you want to flip one of those switches on, Gary? Perfect. All right. So the question is, baseball traveling at 100 miles per hour. Let's make it simple for you. We'll say that that's 44 meters per second. What is the impulse needed to stop the ball? Okay, let's write down the information that we have. Okay, velocity is what? 100 miles per hour, 44.7 meters per second. That is the initial velocity. What is the final velocity?
0.
0. Very important to know that. Okay? That's assuming we stop the ball, right? Okay. So even though it didn't say that, it's implied, so we can write that information down. The weight of the ball is 0.35 pounds, aka the mass of the ball is 0.16 kilograms. Okay? Mass of the ball, 0.16 kg. What force is needed to stop the ball if it is stopped in 0.001 seconds or 0.05 seconds? So we have force at 0.001 seconds equals, we don't know, force at 0.05 seconds equals, we don't know. What do we know?
Acceleration of gravity is...
Time, first, equals 0.001 seconds, and we'll do the other one after that. The other time is equal to 0.00,
Just 1 0.
oh sorry, 5 seconds. So time, fast stop, slow stop, right? Okay, so we know that impulse is equal to force times time. That's one of our equations, so write down the equations. Does that help us? Not exactly. But we also know that impulse is equal to what? Change in momentum, or mv2 minus mv1. Does that help?
Yes.
Sure. Okay. So what is the mass of the ball? 0.16 times v2, which is 0 minus mass of the ball, 0.16 times, what is the initial velocity? 44.7 meters per second. Okay? And we divide that, because it's force times time, we just want force. We divide this by time, 0.001 seconds. And that will give us our force, which is 7,152 what?
Newtons?
Newtons. Is that correct?
Isn't it negative?
Negative. Thank you.
Yeah,
Very
it
important.
is.
What does that negative tell us?
It's just a chart.
The direction of the force, which is opposite of the direction of the movement. Okay? All right, that's force for 0.001 seconds. What is the force for 0.05 seconds? You do the same thing divided by a different time, which is 0.05. What will that give you?
Negative 143.
Well, negative 143 what? Newtons. Okay. Is there a difference there? Huge difference. Seconds. What forces need to stop the ball? Stopped at 0.001 seconds, and then the other one 0.05 seconds. So that's where we got that. Everyone see that? Because MV2, 16 times 0 minus, because it's change in velocity, is minus 0.16 times 44.7. This is a negative value divided by 0.001, so it's going to be negative. What is the negative telling us? Basically, if the ball's coming this way, the force is being applied to the opposite direction. Don't be surprised if there's a problem like this on the exam.
Because these two technically share each other. Force and sine.
All right. What is impact? What is impact? It's a collision characterized by the exchange of a large force during a small time interval. Large force, small time interval. Examples of impacts. Well, we just had one.
Catching a baseball.
What's that?
Catching a baseball.
Catching baseball. Baseball and the glove are impacting. What else? Car crash. Another one. Football players tackling each other. Hockey players checking. Dropping a ball, bouncing off the ground or the wall. If I spit a spitball at your face, would the spitball have a collision with your face? Unless you move, and then it would be against Courtney's face. Which would be good for you, bad for Courtney. Right? So collision. Is there a difference between a ball bouncing and a spitwad smacking you in the head? Other than there's different objects. No? Yeah. One, there's recoil. The other one, it sticks and stays, right? Okay. So, what happens following an impact? It depends on the momentum present in the system. It also depends on the nature of the impact. You said that I was going to do that, so I had to. The nature of the impact. What do we mean by nature of an impact? Is the nature of the impact of a spit wad in your face different than a bouncing ball off your forehead? What's the difference?
If it recoils.
One sticks, the other one bounces off, right? What were you going to say? Sorry, interrupted.
Well, I said the same exact thing.
Okay. And that can be described by the coefficient of restitution. So, what other coefficients have we talked about so far?
Friction.
Which one?
Static and kinetic.
Yeah. Mu. This is different. A number that serves as an index of the elasticity for the two colliding bodies. Okay? And it's represented by the letter E, coefficient of restitution.
What is restitution?
What's this restitution? Well, we can certainly look it up. So to re-restitution, I mean, there's a lot of different. Basically, it's return to. So if I drop a ball, if I restitute it, it goes all the way back to its normal position.
was just